take a look at question 2, the Hertzsprung-Russell diagram is used to classify stars, P, Q, R, and S. Stars in region S of the diagram are much dimmer than other stars in the same spectral class. The property of stars in region X explains their relatively low luminosity. So remember, R is clearly your main sequence. Okay, these are heading towards your giants, as we discussed. They are brighter, but they are cooler. And this is hotter, but less bright. And the reason for that is because they have a smaller surface area. The surface area affects how much energy can be radiated out, according to the Stefan Boltzmann, which we don't study. But basically, depending on how the area of radiation, that can directly affect the luminosity of the star and the power radiated out. Describe two processes which account for the energy production in stars. Okay, so the two processes that you would basically talk about would be, well, the process would be nuclear fusion. But the two processes you would need to focus on, of course, would be the proton-proton chain and the CNO, right? So you'd focus on the fact that you've got the proton-proton chain and the CNO cycle. Now, you want to describe the two processes, okay? So firstly, we talk about nuclear fusion. So you might say something along the lines of nuclear fusion is the process by which multiple smaller nuclei are fused together to form a larger nucleon, losing some mass, and hence releasing energy in the process. For main sequence stars, or even most stars, this is mostly achieved by the proton-proton chain, where 4 hydrogen nuclei are fused into 1 helium nucleus. This is during their main sequence life cycle stage of the life cycle. Now, you'd probably mention the second process. So alternatively, in larger stars, the higher temperatures enable the CNO cycle to dominate, which catalyzes the reaction, okay, and results in faster conversion and higher power output. Something along those lines, right? Like the two processes they're really talking about here are the proton-proton chain and the CNO cycle. They're both part of nuclear fusion, which we've given a brief description about. We've described what type of stars go for proton-proton, which is most stars, and which stars go CNO, which is the larger stars that have a higher temperature. Basically because they're bigger, so their gravity is stronger. Because the gravity is stronger, thus they pull in more, and because they pull in more, the temperature gets higher. Okay, so compare the features of emission and absorption spectra in terms of how they are produced. So remember, with any question about comparison, you want to focus on both similarities and differences. So remember, we understand that emission and absorption spectrum should basically give you the same lines, assuming you've got the same element. Okay. And how do they, and why is that? Well, you might think about the fact that your emission and absorption spectra result from electrons jumping between shells. So you've got absorption when it jumps into a higher energy state, and you've got release, okay, emission when it jumps to a lower energy state. So when we say the features in terms of how they are produced, we probably talk about the production in terms of the transition of electrons between the sort of stationary states in an atom, okay, and then talk about how that relates to your wavelengths. So something along the lines of emission and absorption spectra both are related to the discrete line spectrum of elements, which result from the transition of electrons between the stationary states of the atom according to Bohr's model. So you can use Bohr's model as an example. Okay. Now, emission occurs when an electron jumps to a lower energy level, while absorption occurs when the electron transitions to a higher energy level. Okay. So basically, you've got the emission and you've got the absorption. They both relate to the movement of electrons between stable states, otherwise known as stationary states. So the wavelengths are generally identical. And within your course, there are differences that there is going to be one wavelength that is equal, and then there are minor fine lines, hyperfine lines that we're not going to talk about outside saying that Bohr can't explain them. Okay, so the wavelengths are identical, and this is due to the fact that the energy level differences are equal, and you can calculate it by E equals HF, provides the frequency of the electromagnetic wave. Now, so we really focus mostly on the similarities. We mentioned one thing being different, which is one is when the electron jumps out and one is the electron jumps in. But the question did say how they are produced. We talked about the jumping out and the jumping in and the electricity. I think we would now need to talk more about the fact that, like, how they're actually sort of, I guess, gotten. So we note that emission spectra is often off a black background with specific lines, and an absorption spectrum is typically when you've got a continuous one with certain parts taken out. So we would then distinguish that. So typically, emission spectrum is produced by exciting the sample. So basically the electrons are then excited. So the electrons can then basically fall, revert to a more stable state, resulting in emission lines. This shows lines on a dark background. On the other hand, absorption spectra is done when is produced by passes a continuous spectrum through a sample, which is relatively cool. When we say cool, we mean by sort of versus emission. So it's still a few hundred degrees, but it's still lower. Okay, so it's cool, which then absorbs certain wavelengths. Resulting in a sort of black lines on a dark background, on a colored bright background. So you can see that that gives you the different ideas of the spectra. Okay. Let's work through this one. Hertzsprung-Russell diagram is shown. X is a main sequence star with 12 solar masses, and you can see it's quite high class and quite bright. Describe how star X will change physically and chemically as it continues to evolve. The 4 marks. Okay, so all you basically need to get from the Hertzsprung-Russell diagram is basically what type of star is star X. Okay. Now, star X being 12 solar masses, it's probably going to be big enough to become a black hole. So we will basically talk about how this changes. So right now, star X is a main sequence star. But of course, because it's a main sequence star, it's going to run out of hydrogen to convert into helium. So at some point, okay, it will then run out of hydrogen and start, I guess, not being able to, the inside will start collapsing and the outside will expand. It'll become sort of a red giant. Okay. And that red giant will then be quite bright, okay, and quite large, while it fuses the helium into, I guess, carbon and so forth. And then as the temperature will then get hotter, and it will keep fusing until iron because of the mass defect. And ultimately, it will then, I guess, create a supernova and then form a black hole. So that's the general description. So X, currently main sequence star, burning hydrogen. What it will then become is a red supergiant. Now it's going to become a red supergiant because, well, it's going to run out of hydrogen, and that means you're going to start fusing helium. Okay? And ultimately towards iron. There's a lot of various steps that get there. And that's the chemical aspect. But of course, in terms of physical size, then this will become larger. and cooler. All right, well, the inside the core will become hotter. That's the surface temperature cooler, but the core will become hotter, allowing more and more fusions to heavier elements. Ultimately, it will then have a supernova and explode, and the inside will collapse to a black hole. So that hopefully clears up how to do that. Okay, explain how blackbody spectra, emission spectra, and absorption spectra are used in analysis. Okay. So for 7 marks here, maybe it'll be easier to type this, but for 7 marks, you want to explain how explain how blackbody spectra, emission spectra, and absorption spectra are used to analyze the surface temperature and chemical composition of stars, and you want to make reference to your different observations. So let's think about how we would answer this question. And explain about blackbody spectra, emission spectra, and absorption spectra for specifically the surface temperature and chemical composition of stars. Now, this is a question of the old HSC syllabus. Okay, so for 7 marks, you only need to talk about those, but you might also think about what else under your current syllabus that you can also talk about, such as translational velocity, rotational velocity, density of a star, for example. Okay, but for this question, we're limiting ourselves to surface temperature and chemical composition. Okay, so we have all right. So blackbody spectra, how does that help? Well, we probably need to think of how that's related. So we understand blackbody is, well, basically a model for an ideal absorber, and that allows us to get a relationship between the peak wavelength observed, with peak wavelength meaning wavelength with highest intensity, for the temperature. How does that relate to what we're saying? Well, I guess we basically can model the star as a black body. And therefore, we can then, by observing the spectra of the star, we can identify the peak wavelength from the spectrum emitted by the star. Okay. So we basically take the light from the star, we spread it out, we get a spectrogram, and then we'll get the spectra of the star and the one with the highest intensity of the peak wavelength. Okay, so with that in mind then, if we have the peak wavelengths, then, well, we can use then Wien's law. So basically, we've got, as temperature goes up, wavelength goes down. To calculate the wavelength, the temperature of the surface. Now, we also need to talk about emission and absorption spectrum in terms of chemical composition of stars. So we understand that the emission spectrum is unique to each element. This can be explained by using Bohr's model. So for 7 marks, you do a little bit of explanation of emission spectra, and then you relate to absorption spectra in a moment. So Bohr's model of the atom postulated that electrons remain in stationary states, but can transition, which are of fixed energy levels for each atom, but can transition between these states through the emission or absorption of electromagnetic waves. The emission spectra is a result of electrons transitioning from a higher energy level to a lower energy level. And we might explain a little bit about the line spectrum. So for a particular atom, because the energy levels are fixed and discrete, the difference between the energy levels are also discrete. Using E equals HF, we then find the frequencies, and therefore wavelengths of the emitted waves are also discrete, resulting in line spectra. Importantly, though, because we're trying to talk about chemical composition, importantly, we need to talk about how it's different for each element. So, importantly, the line spectra is unique to each element due to the different energy levels as a result of the change in the nucleus. Right? You've got a hydrogen, which is 1 proton, you've got a helium, which is 2 protons, and so on and so on. So because the nucleus has changed, the energy levels have changed. Because the energy levels have changed, the difference in the energy levels have changed. So the frequencies have changed, and the wavelengths have changed, so your line spectrum is different. Okay? So therefore, on Earth, we are able to determine the line spectra for each element. Now, in stars, the core emits a continuous spectrum as per the blackbody assumption. So it gives a continuous spectrum, but the gases in the outer parts of the star absorb some of the spectra according to their chemical composition. And because you are absorbing it according to the chemical composition, then as a result of that, you're going to end up having an absorption spectrum. So the spectra received on Earth is an absorption spectrum. But you just now need to compare that the lines in the absorption spectrum against the line emission spectra that you've got here by comparison of the wavelengths, which may include redshift. So you might need to account for that. We can then identify elements and chemical composition of stars. Right? So basically, we talked about how black body relates. The black body basically relates to the core giving out a black body. And as a result, we can calculate surface temperature quite easily. And with that assumption as well, because we know it gives out the sort of black body radiation with those sort of curves and those intensities, we can then assume it's got a continuous spectrum, which then means that when it's absorbed, as we talk about here, then because it's absorbed, then we know there should have been spectrum there, but any weaker parts were due to absorption. And that relates to our understanding from emission. So something like that, something like this, we'll talk about that. Now, what I probably need to add in my answer, if you read the question, is refer to observations that can be made in a school laboratory. So I've spoken about this very generally for now. I haven't really tied it to specifically observations made in a school laboratory specifically yet. So I'll probably need to add some more specific references to observations made in a school laboratory. So you may have done similar observations, either when you did, well, you may not have done too many excursions this year, but, or maybe early in the year you may have, but the idea is that you can actually observe these line spectra. So we might talk about, we might add a section here. So here's the theory that can force model. Okay, so we might add a section here about the observations. So this can be observed in a school lab using basically equipment. So using prisms to observe the line spectra after diffusing the emission output. So school labs have, and some schools have have excursions in universities to do this. Basically, you've got, or basically an emission spectra, right? You heat it up, you describe the apparatus, right? You heat up to excite the gas. It gives out an emission spectrum. You then pass it through a prism to diffuse it, and then you basically then look at the particular wavelengths. Okay. So basically, something along those lines should be something that you might want to write for an answer like that, with a bit more reference to the school laboratory. Okay, so again, back to stars with the HR diagram, absolute magnitude spectrotype. Outline the differences in the stars, in the spectral stars between X and Y. Okay. Well, you'll notice that both X and Y are on the main sequence part, right? And they're in sort of class B, whereas Y is, I guess, sort of M. So we would expect that the color will be quite different because the temperature is quite different. So if they want us to outline the differences in this, but they specifically want us to outline the difference in the spectra of X and Y. So you can see X is much hotter, and thinking like a black body, a much hotter one will look much bluer. And it will also have sort of a stronger UV component. Whereas Y will have a much redder lines and will basically have much less UV. Okay, so something along the lines of, we'd expect X will have a largely blue dominant spectrum due to the high temperature. and have He ion lines and more UV. Y being a lower temperature main sequence star, noting we want to outline the differences. On the other hand, just to make a point that we're making we're talking about the differences, Y has a redder spectrum due to the lower temperature with molecular lines would be the key point there. You may also see some other lines, but I mean, that would really be the key point. Molecular lines, and possibly at that point there. I mean, it's an M, and it's quite low. It's main sequence. So we can leave that like that. Okay, explain how gravitational forces affect star death through a range of solar masses. So this is basically talking about the life of stars. And again, there's a 6-mark question. So you basically want to talk about, well, how the star life cycle, the different types of star life cycles. Now remember, star life cycle is very much dependent on the mass of the star, because that basically determines what's going to happen there. So think of what would say that. So gravitational forces affect star deaths. Okay. So I don't think you'll quite get the exact same question under the new syllabus, just to be clear, because this would have been taken more from the astrophysics from the older syllabus. So I don't think you need to know it into that level of detail, not the same level of detail. But essentially, when we talk about star deaths, we understand that the gravitational forces, so a star life is dominated by the forces that it is subject to. Of key concern is the gravitational force and the radiation pressure. During the main sequence hydrogen fusing stage of the star's life, the radiation pressure is equal to the gravitational force pulling in. Thus, an equilibrium is established. However, as the amount of hydrogen decreases, the radiation pressure decreases, resulting in a compression, or basically contraction, in the core. This thus increases the temperature further and causes the helium to fuse. This proceeds until fusion to iron is achieved, which is the highest binding energy per nucleon. if the star is sufficiently massive, this will still be insufficient to prevent gravitational collapse. So in this case, this means the core will collapse. Well, basically this means the star will undergo a supernova and thus become a neutron star. This is when the gravitational force pulls the star together to forming the electron, essentially electron degeneracy, meaning electrons can no longer exist independently with neutrons only. For even more massive stars, electron degenerative is insufficient to prevent collapse, and that would require, that results in the formation of a black hole. We also need to talk about white dwarfs. So as the amount of hydrogen, yeah, for sufficiently massive, yep, for sufficiently massive stars, this produces until fusion and so forth. And basically, if the star is not that big, let's expand this a little bit. If the star is not too massive, the successive nuclear fusion reactions will be able to balance out the gravitational force. Thus, no further collapse or contraction in the core, maintaining a basically balance. And this is a white dwarf. But if it's more massive, it's still it's not enough, even with getting all the way to hydrogen, and there's no further sort of fusing available. So that means it will undergo a supernova and therefore become a neutron star. And that's when you rely on electron degeneracy to keep the star sort of open and not radiation pressure. But for even more massive stars, even that's insufficient, and that would then form a black hole. Okay, describe how the spectrum of the star. Okay, so we basically did this question, so we can just skip that. Describe how the distribution of stars on Hertzsprung is the process that occurred during the evolution. Again, for 6 marks. So you can see there's a lot of sort of extended response questions here. We've done a lot of star ones, so let's see if we can jump to a few of the other parts because there's more to module 8. But you can see there's a decent number of star ones. And a lot of these are from the astrophysics. Well, they are from the astrophysics from the old syllabus. So don't expect to get exactly the same ones, but certainly focus on ones which talk about the spectra, which is ones you're more likely to, and so physical characteristics and motion. So that's something that's much something that can definitely be asked. Okay, so absorption lines. Okay, we did a similar question to this, I believe. That was probably part of a small multiple choice. So that's still all stars. Okay, so here is your questions on your atoms. So after DC voltage, you've got hydrogen gas separated into streams of positively charged particles. What we concluded from this observation? Okay, well, you're applying DC voltage containing hydrogen gas and it's separated into streams of positively charged particles. So hydrogen gas conducts electricity, well, clearly doesn't. Yep, so what that would then suggest is that it's made up of charged, like it's got components which are charged, right? Because you can separate it into, I guess, a part that is positive and a part that is negative. You started with one thing, you ended up with more than one, so it's split up. What if the following is true in relation to all drop experiment? Aim of the experiment was to measure the charge of the electrons, and the field used was just electric to keep it up. 3, in an experiment, an electrical charge or droplet was suspended in air by an electric field. This is definitely Millikan's experiment related to it. So if more drops were suspended and measurements taken, which of the following properties would all the operands be observed? We don't know that the mass is definitely not all the same, but what they're really testing on is the fact that the charge of each drop would be a multiple of a fundamental charge, C. Explain how quantitative observations contribute to the development of the concept that certain matter and energy are quantized. For 9 marks. Okay, so we're talking about energy is quantized. So that's really going to be referring to, I guess, just running through some ideas here and trying to get through some more questions. This will be really referring to Planck's idea and Einstein's photoelectric effect, which is from an earlier module. And then you want to relate the development of the concept that matter is, I guess, quantized as well. Well, I guess if you have the idea that energy is quantized and you've got mass energy equivalence, then you've got E equals mc squared. And if energy is quantized, then it would also indeed suggest that matter in a way is quantized as well. So let's okay. Now, we also have the idea, of course, that you've got, well, quantization of matter. I suppose we're talking about it in terms of particles, right? So we also have the idea of electrons being discovered. So that's your cathode ray experiments. We're saying that your matter is in terms of certain particles. Okay. And that, of course, also relates to, I guess, Millikan's experiment. As well as Thomson's experiment, where together you're able to calculate the fundamental charge, which indicates that, well, if there is a fundamental charge, that suggests that there is a fundamental particle that has that charge, and you're always in sort of multiples of that. And in addition to that, we've also determined the charge of that particle from Millikan. And because we've got the charge to mass ratio, we also have the mass of that particle due to Thomson and Millikan. So that's kind of the suggestion there. Those would be probably the key ideas you would talk about, but there are other ones you could talk about as well. I mean, you could talk about, I don't think you need to talk about everything because there's too much to talk about, but you could talk about, I guess, Bohr's experiment in terms of, I guess, the line spectra, which indicates, well, energy is quantized. There are a few more things you could talk about, but I think if you just pick 2 or 3, right? For 9 marks, pick 2 or 3, talk about them in depth, and show how those things, so you could pick, for example, I mean, Planck's, Einstein's photoelectric effect. That's already 2. You can maybe talk about cathode rays if you want. Like, we've given at least 4 to 5 ideas there. Just pick 2 or 3, talk about them in depth, write the analysis of quantitative observations. So you've got to focus on the analysis. So for whichever one you write, you need to actually talk a bit about the analysis. So how did Planck analyze his? How did Einstein analyze his? How did Thomson and Millikan analyze theirs? All right. And then you're going to need to talk about the development of the concept that certain matter and energy are quantized. Well, we kind of gave you a brief flavor of this. And you can see this is a very broad, as far as the question you get, this is not specifically one module. This is the general idea of from module 7 and 8 together. How did this contribute to our idea that energy and or mass are quantized? And you just need to draw on material and content that you've learned, focusing on talking about them in depth to justify how scientists came up with the idea and the evidence that supports that the matter and energy are quantized. Okay, so this one, diagram shows an apparatus used to investigate subatomic particles. So if you take a look at this, you may or may not recognize what it is, like whose experiment this is. This is one we didn't spend too much time talking about, actually. But basically, we've got a vacuum pump with a polonium source. The whole point of the polonium source is that it emits alpha particles. The alpha particles go through a beryllium window. So something happens, which then hits the paraffin, and something happens, and then we recognize that a proton is here, and they can be detected by a Geiger counter. Now, it says, how did Chadwick use a law of physics to identify a property of X? So think about what we've learned. Chadwick is really, for your course, only known for one thing, right? So that should help you identify what this is about. And then once you understand what that's about, then that means, okay, you need to know what X is. And how did he do it, right? So what basically Chadwick did is Chadwick discovered the neutron. Okay, so X is the neutron. So how did he discover the neutron? Well, through calculations of the momentum of the alpha particle, the unknown particle, X, and the protons. By assuming, and you have to say this, conservation of momentum, right? What did he really find out about the neutron? Well, he found the mass, right? he found an uncharged particle with similar mass to the proton, which we call the neutron. So that's basically Chadwick's experiment. He uses a polonium source, emits alpha particles. Okay. These alpha particles then knock out some particle that was as yet unknown. Okay. But the problem with these particles, being neutrons, is that they're not charged. Now, if you don't have a charged particle, then it basically can't really directly detect it, because most of our detectors rely on charges. So if it's uncharged, well, then there's not a whole lot you can do. So what we end up doing is we convert this uncharged particle into a charged particle. We send these uncharged particles into paraffin. And when a neutron hits paraffin, it may knock out a proton instead. Okay? Basically because, well, I mean, we are aware now that this mass is roughly equal to that mass. So because the masses are roughly equal, then from your basic era, like module 2 with conservation of momentum and collisions, similar masses can give you a lot of energy across. So the neutron can knock out a proton. We detect the proton. We do some calculations to then work out that this has a mass roughly equivalent to a proton, and that was an unknown particle at that time, and thus discovered what we now nowadays to be the neutron. Okay. All right. What does the Maltese cross demonstrate about cathode rays? Well, the Maltese cross is just a cross, as we said, which gives you the shadow. So it tells you that they travel in straight lines. In fact, I think we did this question in the other section. So this is just, yeah. Which diagram clearly shows deflection of a cathode ray by a bar magnet? So if you get a question like this, just recognize that that's the North Pole, that's the South Pole. This is, remember, a cathode ray is an electron. So the electron, this is negative, of course, this is positive. So that's weird. That's the negative, that's the positive. I mean, I think they intend for the electron to be going to the right. But they've not really connected the electricity the right way. I mean, this question really should, I mean, the way it's written really appears that, oh no, okay, that's okay. The electron is going to the right, as I was saying, but what's basically happening is, if we enlarge it, just to be clear, so what's basically happening is, this is your electron gun. Okay, so it's not, yeah. So you've got your, they've left out the components. So what they're really talking about is, this side is indeed the positive end. So it's a bit like what we did with our linear accelerator. This is our positive end, this is our negative end. They've left out details, okay? Here is basically your electrons are emitted here. And as a result of the electrons being emitted there, you want them accelerated to the right. So that means your electron, as I was saying, is heading rightward, okay? Which is what I expected, but yeah, that's basically, collectively, this is an electron gun, of which they've left out the details. Okay, so the key important point you need to get from here is that the electron is pointing outward. Now this magnet is pointing like this. So just need to understand that the magnetic field is well, you understand the magnetic field is going like this, right? But as far as the electron is concerned, it's going into the page. Okay, so if it's going into the page, then you just take a look and see what happens. So electron going to the right means positive charge going left, and it's going into the page. So actually the electron should curve downward, which is not what you see here. So zooming back out, if the North Pole should make it zoom downward, then that means you need B. Because if the North Pole is here, that means the South Pole is there. The South Pole is there. The magnetic pole has done. These will definitely be wrong because the force is always perpendicular to the magnetic field, not toward the magnet. This would only occur if you had a magnetic field and you were not a magnet. If you had an electric field where the magnet is, not an electric. These would be like this if you put an electric field where the magnet is, not a magnetic field, which is what you've got here. Okay, so Maltese cross again. Now, which of the following cannot be inferred this time? Well, we can infer they travel in straight lines. We can infer they can't pass through metals. Now, in terms of the Maltese cross, we can't really infer that they possess momentum. I suppose we can still infer they possess energy because of the fact that it would heat up. So I think the best answer here is B. But you definitely can infer that it travels in straight lines. It can't pass through metals, as many of the times we've done these Maltese cross experiments. Nothing moves, so we can't say it possesses momentum. But you can assume that it possesses energy because Maltese cross does heat up. So we've talked about this at quite some length before, so we'll skip that. Calculations are fine. Let's try to get to the next section. Yeah, so this is atomic models. All right. So now you've got the section quantum numbers of the 4 lowest states of hydrogen atom together with the energy of those states. 1, 2, 3, 4. Energy given in joules. What transition will absorb a photon of wavelength 102 nanometers? So this just needs you to do calculations with E equals HF, which is HC over lambda. So quick calculation. Lambda is unknown. Oh, we do know it. 102 nanometers. So it's 1.94 times 10 to the negative 8. 18, which of course is 3, which of course is 3 to 1. Well, that's emission. The question says absorb a photon, which means it's 1 to 3. Okay, so here you've got 8 marks. We've gone through similar questions, so I won't go through this one, but it asks for scientists to use observations and mathematical ideas to improve scientific models. Specifically, you want to talk about the work of scientists who have contributed to our understanding of the atom. So you probably want to think of starting from, say, Dalton, moving on to Thomson. And specifically, if you need to talk about observations and mathematical ideas, so you might want to focus on the sort of observations, in this case, being cathode rays, meaning that it's a component of a atom, and you want to focus, if you wanted to focus on mathematical ideas, then the calculation suggests the fact that it can repel alpha means you've got a high concentration of charge and mass. They can actually calculate that. That, of course, leads then into Rutherford, which is this part. Okay, and you might also focus on the observation of the Geiger Marsden experiment, giving you the calculation. Of course, that has its problems, which were partially addressed by Bohr or improved. For Bohr, you can then focus, of course, on the hydrogen spectrum and the stationary states. You can focus on the Balmer equation. And then, of course, after Bohr, you can talk about the Broglie, where you can focus on his matter wave equation. And then in terms of the matter wave equation, you can then talk about how this was justified in terms of the Davidson-Germer experiment, in terms of diffraction of electrons. And then after the Broglie, then you can have Schrödinger. And that would, which is the understanding of the atom with the mathematical ideas of the Heisenberg uncertainty principle, as well as the Pauli exclusion principle, which then leads into your electron configuration, which is basically how we talk about it. And if you feel so inclined, you can then also talk about, I guess, the competing matrix sort of theory, but I don't think that's really necessary. But you can see, I mean, I'm just giving you in point form at the moment, but you can see why there is significant enough material for 8 marks, right? You want to analyze the way that they used. Make sure you analyze when you're answering this question, not just list like I've done, just giving you the key ideas that you might want to talk about. Which observations did they do? Which mathematical ideas, okay? And how did they improve the model? Okay. I'm giving you ideas of what you can talk about, but again, like we said last time, I don't think you need to talk about every single one of them. The focus of this question is how models are improved, right? They did not ask for the entire development of the atom from Dalton to Schrödinger. But of course, along the way, there have been multiple improvements. For 8 marks, I think you need to say at least more than one, at least 2, okay? At least 2. But pick 2 that you are comfortable with and familiar with, and go in depth and analyze what they observed, what experiment was, what were the observations, and therefore what did that say about the atom model at the time, what was wrong about the model at that time, and what ideas did they then come up with mathematically to then improve the model. So you can perhaps focus on Thomson to Rutherford, Rutherford to Bohr, for example, if those are the ones you're most comfortable with, which is likely the case because they're like ones. So you can say, how did Rutherford improve on Thomson's? Because he observed that the Geiger Marsden experiment observed that alpha particles directed at a thin gold foil were deflected, and the distribution of the deflection angles was unexpected. In particular, although the majority passed through undeflected, some were deflected at small angles, and a small number were deflected at large angles. Now you can then focus on the mathematics. This could be calculated to be essentially impossible if Thomson's plum pudding model was accepted. The deflection of alpha particles at high angles necessitated mathematically that a high concentration of mass and charge was in a very small region of space based on the electrostatic force of repulsion. And that charge will be positive. As such, the idea of the nucleus was born. And therefore, we came up with the Rutherford nuclear model with the nucleus in the middle, with small region of charge, with electrons going around. However, this model still has some issues, such as the fact that the electrons would charges undergoing acceleration, which meant that they were going to be emitting electromagnetic waves under classical theory. And Rutherford's model also had no way to explain the force of why the nucleus is stable despite positive charges being in close proximity, nor could it explain the line spectrum of hydrogen, which was being investigated at the time. And so then you go on to talk about how Bohr improved that. And if you did the same sort of level of detail as I did for Rutherford, roughly, with Bohr, then that should be enough for 8 marks, right? You can pay lip service to a few of the other ones, like you say, this improved on by de Broglie, but definitely you'd need to give at least 2 of these, right? Yeah. All right. So you can see lots to write there. We've kind of talked about the limitations, so let's see if we can get on to the next section. Talk about a lot about this. So, Rutherford model. Okay, so now it's nuclear. You've got a 5-gram sample of radioactive strontium decayed over time. Shows this. Okay, decay constant. I mean, so you just use the formula. Okay, so read off and use formula. Okay, this one you've got natural decay. So you want to work out the mass change in total binding energy. So as usual, the total mass, of course, will decrease and the total binding energy will increase. So here's your line of stability. Okay, so if you've got negative beta decay, just think of what happens to the number of protons and the number of neutrons, which are on your axes. And then that should give you an idea of what's going to happen, right? When you have a beta negative decay, while this is not technically true because it's really due to the weak nuclear force, but in terms of mnemonics, you can think of it as, well, a neutron is a proton plus an electron. So when you get rid of a proton, so neutron minus electron gives a proton. So I know this is not actually true, right? In terms of the way it's made up. We already said a proton is an up, up, down, and a neutron is an up, down, down. So there's no electron in there. But if you think of it for mnemonic purposes, then a beta decay emits an electron. So it starts off as a neutron, you get rid of an electron, so you end up with a proton. So that means the number of neutrons has gone down. So you've gone down by 1, and you've gone minus 1 neutron, and you've got 1 more proton, plus 1 proton, meaning you've gone down and to the right. So it would be A. So half-life, I think you guys all said you were generally happy with. Okay, calculate the energy released. So just make sure that you use E equals mc squared. Calculate E by taking the delta, or calculate M, right? By calculating delta M. You've got the mass in U, convert to kg. If you're not familiar with the units, use a data sheet, okay? And this will be in joules, as you want. Okay, distinguish between the process of nuclear fusion and transmutation. So I don't do transmutation much anymore, but simply transmutation is generally when you, well, make new elements, okay? So usually this is through neutron bombardment with subsequent decay. Okay, usually beta. Nuclear fission is basically when you have a splitting of basically a parent nucleus. And I guess since we're trying to distinguish it, we won't focus on the similarities, we'll focus on the differences. And the differences, of course, would be that for a nuclear fission, you've got, I guess, neutron plus your parent to split up into multiple things, and usually multiple neutrons. For transmutation, you've got neutron plus this to become a new thing with maybe a beta decay. So the difference, of course, is both of them give new ones, but this one aims to split it up. This one aims for the neutron to be absorbed and not split it up into smaller nuclei. And yeah, transmutation is not done too much in the new syllabus anymore. It is still related, but it's not directly tested usually. Calculate energy released. Well, we did something similar to that. Okay, so calculations are quite straightforward. Okay, so if you want an uncontrolled nuclear chain reaction, then the key things would be that you want more than one neutron to be released per reaction. So you got a chain reaction, and you want no control rods. And ideally, you want a moderator to enhance the neutron absorption. So basically, you want the neutrons to be more effective. Okay. All right. How does the equivalence between mass and energy relate to what occurs during the natural radioactivity process? Well, of course, you've got mass lost, energy released, okay, and E equals mc squared. So that's a lot on that section. Let's see if we can get to the next section. Okay, so here you've got a cyclotron invented in 1932, accelerates particle to a very high speed, and shows the basic design. So you've got the D's, got the target. So as we said, you've got the particle accelerated, so it spirals out. And you've got a high frequency alternating voltage. Yep. Okay, explain the physical principles involved in the design of the cyclotron. Okay, we kind of did that earlier. The currently use of the cyclotron in the development of understanding of matter. And okay, let's focus on C. Quarks are the important part of the standard model of matter. The table shows the 6 types of quarks and their charge. Oh, they just asked for proton and neutron. Well, as we said, up, up, down for proton, and up, down, down. All right, let's see if we can find another question. Okay, here, the table below shows the first generation of quarks and antiquarks. So these are the first ones theorized. The standard model states that baryons like protons and neutrons are composed of 3 quarks like mesons are composed of 1 quark and 1 antiquark. So state the quark concentration on the neutron and the negative pion. Okay, so for the negative pion, you've got 1 quark and 1 antiquark. So it's negative. So if it's negative, you have either up and anti-down, which will be +1, or down and anti-up. And so the neutron we already said is up, down, down. But the negative pion, because it's got a charge of -1, it must be a down followed by an anti-up. Because as we said, you can't have an up with an anti-up. That's not a particle, that's a pure energy. You can't have down with anti-down. So the only reason is up and anti-down, which will give you +1, which is not what you want. So it's down and anti-up. As I mentioned before, you do need to know the composition of neutron and proton. We did not memorize the composition of pion here. We worked it out on the spot by focusing on the fact that it's negative and that it is a meson, as stated. Okay, so we kind of talked about this when we talked about it today, but describe how the key features and components of a standard model of matter have been developed using accelerators of a probe. We basically talk about how you use accelerators to collide particles together to then accelerate them to higher energies. By comparing them, by accelerating to higher energies, that therefore allows you to then examine the trajectories of those paths, which allows you to determine, based on the magnetic field and so forth, the mass to charge to mass ratio of those objects. By considering E equals mc squared, you also, like mass energy equivalence, you also get an idea, and based on the energy levels that you're seeing before and after the collision, you get an idea of the mass of those particles. And through repeated collisions and analysis of that data, you then are able to then basically get data to support the standard model of matter. And doing the exam now, you would probably use the Higgs boson as one of the more recent and also more clear examples of such a development. Okay. So those are some questions from Module 8. Hopefully you found that helpful.